Good afternoon. We're happy to have Milo Schield with us to give us his presentation, Two Big Ideas for Teaching Big Data, Coincidence and Confounding. Take it away, Milo.
Well, thank you, Jean, and much thanks to Jean and Michelle for heroic efforts in trying to make the webinar work despite the technical difficulties. That's how we move forward in statistics education. We started it off with the survey, how many participants were online. There were about 54 participants. And I asked, who chooses your statistics text? And about 54% said the teacher, 42 said the teachers together, 29 said somebody else. Obviously, the answers weren't exclusive. When I asked what fraction of a one-semester intro course should focus on coincidence and confounding, 31% said the minimum. And that's probably where I'd be. I just don't have time to put another topic or two topics into my overloaded intro course. 44% said they'd go to the next category, 5 to 15%. 19% they'd go up to 30%, and the remainder said they could go over 50%. Well, it all depends on priorities, and I'm here to talk about making coincidence and confounding a priority for your intro course and for big data. So, big data. For me, big data is any data set in which all the associations are statistically significant. This means that statistical significance doesn't have much value with big data. But in big data, coincidence and confounding are typically the big statistical problems. Now, I have a true confession. I've been teaching statistics a long time. I've always talked about association as not causation. My examples always involve confounding. The Berkeley sex discrimination case, the ice cream and burglaries in the summer. But my course never involved confounding. It was all about randomization, sampling error, margin of error, confidence intervals. In a sense, I was guilty of bait and switch. I brought them in with one kind of problem, example, and then I switched to another. So I want to show you how I start my course now using coincidence. But first, another poll, because maybe I'm missing something. I asked those in attendance how many intro textbooks use coincidence or chance to support the claim that association is not causation. My answer is none. But only 6% of the respondents agreed with me. 41% said they knew of 1 or 2 books. 24% said they knew of 3 to 6 books. 29% said they knew more than 6 books. Now, either I'm not well read, or I've written the question wrong, or something. So send an email to shield@augsburg.edu giving me some textbooks, because I certainly appreciate getting an education. Now, back to coincidence. Coincidence is an unlikely combination of events that's memorable. Did you notice when you watched the wedding ceremony, the similarities? Of course, I got these off the web, and maybe these are all Photoshop for what I know. But coincidences are memorable. We all have stories. Now, how are we going to demonstrate a coincidence in a classroom on demand every time? That seems impossible. But I'm saying it isn't. And I want to bring up 3 cases that I used to start my intro stat course. The run of heads, the grains of rice, and the birthday problem. Now, we all know about a run of heads. Auditors use the absence of a run of heads as a sign of fraud. What I did was to create an Excel spreadsheet. The link's at the bottom. You can download it, have your students run it, have fun with it. It's a simple spreadsheet. It's got a random between function, puts up either a 0 or a 1. A 0 is a tail, a 1 is a head. If it comes up 1, then the conditional formatting fills in the cell with red. If you get a number of heads, a number of red cells touching, you have a run. And so in that row 4, we have 4 heads in a row. That's our run. And over to the left here, you see that number 4 in green? That's the length of the longest run in that row. Now that you understand how the spreadsheet works, let's take a look at the full spreadsheet. Here in the top row, we've got a run of 4 heads, 1 chance in 16. In this row, we've got a run of 19 heads, 2 to the 19th, a chance, 1 in over 500,000. We pressed F9, we got 19 heads in a row. That's a 500,000 year flood this year. The students enjoy pressing F9 because here on the left, we've got the biggest run in a row, and at the top, we've got the biggest run in the spreadsheet. Well, let me just show you for a second. Here's the spreadsheet. You refresh by hitting the F9 key. F9. 10 is the longest run. 8 is the longest run. 9 is the longest run. 11 is the longest run. Can we get bigger than 11? Well, you get the idea. But these students are getting these 13. We got a winner. Students love playing with this. They're dimly aware that these are amazing coincidences and they're happening every time. Hold that thought. So supposing we ask them, what's the chance of a run of 10 heads? They don't realize the question is ambiguous. It doesn't state the context. That if you talk about the chance of 10 heads on the next 10 flips, that's your 1 chance in 1,024. But if you ask, what's the chance of at least 1 set of 10 heads somewhere, when you're flipping a lot of coins, a lot of sets, say 1,024 sets of 10 coins each, well, you expect 1 set to pop up with 10 heads. And it can be shown the chance of this is at least 50%. Schield 2012. We can diagram the stuff. As mathematicians, we're oftentimes interested at the point where it crosses 50%. I'm not interested in that point. My students can't remember the math, but they can remember what's expected. That if it's 1 chance in 1,024, and you do it 1,024 times, then it's expected, and it's at least 50%. They can remember that. So this is the first example of coincidence creating an association. My second example comes from Blastland's great book, The Tiger That Isn't. If you haven't read the book, I encourage you, read the book. In that book, he talks about scattering rice on a floor, a two-dimensional surface. It says people can often see memorable shapes. Well, I built this Excel spreadsheet to do exactly that. Let's take a quick peek at that. Here's the spreadsheet. Each cell has 1 chance in 10 of coming up with the numbers from 0 to 9. If it comes up with a 9, it's conditionally formatted in red. I call that a grain of rice. So what's the chance of these 2 cells touching? Well, it's 1 chance in 10 times 1 chance in 10. That's 1 in 100. Really? How about this? We have 3 cells touching. What's the chance of that? 10, 100, 1,000. 1 chance in 1,000. Really? Isn't that interesting? Well, how about this? We've got 1, 2, 3, 4 cells touching. 10, 100, 1,000, 10,000. That's incredible. But up here, 10, 100, 1,000, 10,000, 100,000. 1,000,000. Students love pressing F9 to see what they get on this spreadsheet. Now, there's no way for me to tabulate the length of the longest run, so the students have to paw through and see what they get. But again, they're seeing amazing coincidences every time. Next, number 3, the birthday problem on Mises, 1938. Now, you and I know that with 23, 24 people, we can get it. But I'm not interested in the heavy math side. With 28 people, there's 365 combinations, more than 365. A birthday match is expected. Now, just because I can prove the combinations doesn't mean my students understand it. I want to show them. And so I've created a spreadsheet that you can download that has 7 people on 4 sides of the table. You hit F9, they all get new months, new days. No, I didn't work out February. I think all the months have 30 days. You can improve it if you want. Now you see here, there's a cell highlighted with a number 3. I've got the 4 quadrants, 1 in the upper right, 2 in the lower right, 3 in the lower left, 4 in the upper left. Quadrant 3 has a match between the October 11 birthday here, the October 11 birthday here. Now, how many combinations are there? 7 people on the top, 7 on the right. 7 times 7, that's all these cells. There's 49 for each of the 4 quadrants. That's almost 250 combinations right there. Students can see that quickly. Now, here's another kind of combination. It's not a quadrant combination. It says this December 9th has a match on the west side. Oh yeah, there is a December 9th that has a match on the east side. This isn't a quadrant match. This is an opposite side match, but it's 7 by 7, 49. We've got a left-right combo, a top-bottom combo. We've got almost another 100. We're up to 350. And then if you do the combinations where they get the same 2 people on the same side, you're over the 365. Once students see 365 combinations, they say, got it. Something that happens with 1 chance in 365 is expected. Now, does that mean they understand that association is not causation, that it could be spurious or coincidence? Not really. They just had the examples. To me, they need an integrating principle, what I call the law of very large numbers. Now, this isn't just the law of large numbers. It's the law of very large numbers. In its qualitative form, it says the unlikely is almost certain given enough tries. In its quantitative form, it's saying that if you have an event with 1 chance in n, and you do it n times, that event is expected. And you say, well, sure, it's expected. The binomial theorem shows us that. And, this is the critical part, it's more likely than not. Schield 2012. These are things my students can remember. Now, we've looked at coincidence. What are the outcomes? Well, the students must see that coincidence may be more common than expected. That it depends on the context. Is it before or after the fact? Before we did the target shooting or after we hit the target, now we paint the bullseye. It may be totally spurious, but it may be a sign of causation. That pump handle should remind all of us of an important event in our history, the history of statistical education, certainly. There's a pump handle in London, Broad Street, where Dr. Snow said this amazing grouping of deaths around this pump handle could be coincidence, but it could be causation. Okay, that finishes our section on coincidence. I wanted to ask whether people would teach this. We're going to have to move on to the second half of this talk, confounding. Now, what do we know as sample size increases? 1, the margin of error decreases. Coincidence increases. That was what we talked about before. Becomes more likely, certainly. Confounding remains unchanged. Just because men are more likely to die of lung cancer than women, with a group of data, and we go out and get more data, that doesn't mean we're going to discover any confounders as long as it's just more records of the same kind. If we never ask, are you a lifelong smoker, we wouldn't understand how this difference in gender and lung cancer death association might be confounded by which gender is more likely to be lifelong smokers. So big data doesn't minimize confounding. If anything, big data gives unjustified support for associations. Associations that are really spurious, but it's not chance spurious, they're confounder spurious. But in the end, they're spurious. So what I want to do is move to the most critical, I'd say, certainly the most interesting example of confounding, and that's Simpson's paradox. That's where you have a sign reversal when you take into account an extraneous factor. My two claims. One, a Simpson's paradox reversal is incidental when you're modeling or forecasting, but it dominates when you're searching for causes. To show this, I want to use an example from NAEP data. 2001 math tests, grade 4 in the U.S. I have the data for two states, Utah and Oklahoma. Now you can see that Utah students, 228, did better than Oklahoma students, 224. But you can also see that if we divide the students into two groups based on their family income, the students from high family income did better, 239, than the students from low family income. Now here's the source on the data, and I created a set of 300 records that provides these statistics. And then I went in and did a regression. I want to forecast. The first regression I did on the left side here is just on state. R squared was 0.02. It's about as low as you can get. The p-value, on the other hand, for state was statistically significant with 300 observations. Now, typically adding more factors improves the quality of the model. And I would expect that to happen here. So I then did a regression including income. Look what happened to R squared. It increased dramatically. Whereas the standard error and the p-value of our state decreased. The model has improved in quality. Do we care that the sign of the coefficient on the state changed? On the left side, it was negative. On the right side, it's positive. But as far as the quality of the model is concerned, we don't care. Now, let's talk about explanation. We've got the same data. Now we're realizing that in Utah, almost 80% of the kids were from the high-income family, whereas in Oklahoma, less than 25% of the students were high-income. Now when we ask the causal question, which state has the better education system? If we regress just on state, Utah's better. But if we regress on state and income, Oklahoma's better. It really matters what kind of question you're trying to answer. Most of the students studying statistics are in the social sciences, business, economics, sociology, social work, education. They are dealing with observational data. Confounding is the biggest problem they have. Our statistical education textbooks for the intro course are silent on confounding. I think this is professional negligence. And with big data, we've got to take it on. On the other hand, there are two big reasons not to talk about confounding. The first is disrespect. A colleague of mine said students might have less respect for our discipline if they knew how easily statistics and statistical significance could be changed by taking into account an extraneous factor. We don't want to bring our discipline into disrespect. Secondly, we don't want to model bad practice. There are prerequisites to doing confounding. Confounding is multivariate. That means multivariate regression. That means assumptions. That means a second course in modeling. We don't have time for this. So here's two big reasons not to teach confounding. And they've got to be overcome to introduce it in the intro course. Here are the two rejoinders I see. First is the cornfield conditions, Schield 1999. They set a minimum on the size of confounder that can negate or reverse an association. A butterfly flapping its wings in the Pacific can't reverse all the associations in the world. It has to be a very big butterfly. And this is how Cornfield refuted Fisher's objections when Cornfield argued that smoking caused cancer. These conditions can offset the excessive skepticism and cynicism. Secondly, what about the assumptions, the diagnostics? Well, when the predictor and confounder are binary, the assumptions vanish. The model is fully saturated. You don't have to check assumptions. And there are graphical techniques that allow the students to work the problems without needing any software. I've taught this material for over 10 years to students in English, art, and music. They can work problems on the final exam involving confounding. I'm going to quickly show you examples of both of these with references that you can pursue. Take a look at this set of data. We've got death rates at the city hospital, 5.5%, 3.5% at the rural hospital. You don't want to die? Which hospital are you going to go to? The rural hospital. They probably have cookies and ice cream in the afternoon. City hospital, lots of weird diseases in those big hospitals. On the other hand, on the right side, we notice that the death rate among patients is higher if the patient is in poor health than if they're in good health. In fact, this difference, 4.4 percentage points, is bigger than this 2 percentage point difference. Relatively speaking, the difference is 230% greater, more likely, versus 60%. Cornfield worked out mathematically. If you want to nullify or reverse an association, the confounder must be bigger than the association. Smaller won't cut it. Students, again, can work problems with the simple Cornfield condition. Number two, if you have a binary predictor and confounder, Howard Weiner did statistical education, a great service when he broadcast this technique, a technique that Larry Lesser had identified even earlier. Look at Schield 2006. I've got an audio presentation that takes you through step by step along with some slides. Students can see how an association of rates, of percentages, can be reversed, something they've never seen in any math course. And they can work problems. So, in conclusion, many, if not most of the big data users, and certainly most of our students, want causal explanations. That's what we call business intelligence. Modeling and prediction are just a means to this end. To be relevant for these users of big data, we must focus more on coincidence and confounding. These are the big influences. Our students really deserve a broader education than what we've been giving them. And we must say more about causes than simply association is not causation. We need to introduce confounding along with the Cornfield conditions and standardization so our students can work problems. Now, I had some questions, but don't have time for those. Here are the references to the Schield papers, 1999, 2006, 2012. They cover all these topics. And if you want some other reading, I strongly encourage you to take a look at Judea Pearl. He has a lot of material, but there are 3 articles in particular involving Simpson's paradox that you really need, 2 that involving Simpson's paradox, and the 3rd which I think is an absolute gem on statistics and causality, separated at birth to reunite at this time. This is what I think will mark statistics education for the 21st century. Gelman's blog is an interesting case study in how two people talking about Simpson's paradox were talking at different levels. One at the modeling prediction level, one at the causal level. So, thank you very much. A copy of these slides will also be posted and a transcript will be available. I look forward to any questions you might email me at shield@augsburg.edu. I hope you get a chance to take a look at this presentation before the panel coming up on Wednesday at ECOTS where we talk about big data. Thank you very much.